Okay, here we go. Second video for dealing with Calculus 12, 7.4 applications and trig derivatives. We're going to look at example 3 and 4. Here's the first example. Use local approximation to find the approximate value of sine of 0.2. Again, as soon as I see local approximation, I think two things. Math girl, and I think tangent lines. So when I think tangent lines, I think of this, personally. Then I also think about, okay, what function am I dealing with here? Well, this is the function that I'm approximating, so obviously the function that we're dealing with is sine of x. At what value are we close to that I know the sine of? Well, 0.2 is really close to 0. So this would be around 0 where I would build this. So I'm going to build the tangent line for sine around 0. So what do I need? I need the derivative. Derivative of sine is cos. I need to evaluate that derivative at my point of interest. So cos of 0 is 1. So now I know the slope. And then I need, well, x1 is x0, which is 0, and y1 is f of x1 or f of x0, which is sine of 0, which is 0. So now I know all the data. Y minus 0 equals 1 times x minus 0. So it's not the most exciting. And I would think about, what does that mean? Like, what did I just do? I just did that, but what is the meaning of that? Well, I've got my sine graph. We've just worked out the tangent line at 0. Does it look like the tangent line would have an equation of y equals x-ish? Yeah, it does. So the linear approximation is actually this. X, which is my local approximation, is approximately equivalent to sine of x near x equals 0. So now what does that tell me? That tells me if I want to work out sine of 0.2, sine of 0.2 is approximately equal to 0.2. That's why for small values of the angle, if I go sine of 0.2, degree or radians, because it doesn't matter, 0.2 is close to 0 for both radians and degrees, you get an answer that is close to 0.2. I guess more specifically it should be in radian mode to be. There we go. Sine of 0.2 is 0.2-ish. So there's my answer. That one's almost so easy it's hard. It's almost like what were we doing? And remember the other formula, if for those that were local approximation formula people, we used the one where it said the function was approximately equal to f prime of x naught times x minus x naught plus f of x naught. You might have memorized that formula. I'm not really a fan of that. To be honest, I didn't even memorize that now. I kind of cheated and used the tangent line to build it. So I don't memorize that personally. Next example, one of my favorites, is the question about a rocket taking off at a constant rate. A little bit fake in the sense of it's assuming that it's at this constant rate. Now that would be like right from the get-go, the rocket would be going 50 meters per second. That's a little unrealistic because I realize in real life the rocket accelerates from 0 to probably some kind of terminal velocity. So here we're assuming though it's a constant rate, although to extend it to the real thing would just be just a small level of increase. The rocket is perpendicular to the ground. Again, that also is slightly fake if you watch the NASA takeoff, so the rocket kind of goes at an arc. Here it's presuming it's straight from the ground. And then there's a camera. So let's just draw what's happening here. You got this flat ground. You've got a rocket that's starting here, let's say, and it's taking off. There's my rocket. Looks like an outhouse. Actually, let's make it an outhouse. Put a little moon on there. There's a little. Okay, so it's a flying outhouse. It's going up, increasing at a rate of 50 meters per second, perpendicular to the ground. a camera which is 20 meters from the launch site. So we're assuming the ground is flat. This is 20 meters, and that's always 20 meters. You've got a camera here that's filming the rocket. And then the angle is changing. Because if you think about that, in the beginning, you're going to be changing the angle quite a bit. But then as the rocket gets higher and higher and higher, you won't have to move the camera as much because it's higher and higher up. And what else do we know from the launch site is stay focused on the rocket at what rate in radians per second. So at what rate will the angle be changing? At the instant the rocket is 100 meters above the ground. So I'm going to call this variable here because that is changing. Let's call that y. So we want to know when y is 100, how quickly is that changing? And what else are we given? And we know that dy dt, the change in the y is 50 meters per second. All right, so we've got all the data, taken all the English, put it into kind of math talk, got a picture. What relationship links those together? Well, in my opinion, most of the time it would have been Pythagoras, but because there's an angle involved now that brings out sine law or SOHCAHTOA or cosine law. Right angled screams SOHCAHTOA. And I would look at this and say, first of all, I don't care about the hypotenuse. So this screams sine. I'll write it down here. Sine theta equals y over 20. And then there's my relationship. I might make it look a little cleaner like this. Do a little quick cross multiply. If I took the derivative of this, would I be happy? I'd be getting out thetas and d theta dt's with respect to time, but I'm okay with d theta dt's because I want it. Am I okay with thetas? Yeah, I'm okay with thetas even because I can even use this to solve for theta at any time, at any y that I want. And I'm okay with dy dt's because I have a dy dt. So remember, this is, so picture, information, relationship. From there, what are we going to do? We need to, at that point, take the derivative. So take the derivative, and derivative is 20 cos theta times d theta dt, because that is the derivative of the inside, equals the derivative of y with respect to time is dy dt. And at that point, we are going to solve for d theta dt. D theta dt is dy dt divided by 2 cos theta. So do I have everything to solve this? Let's see. I have this. Check. I don't have theta to get cos theta. Could I get that? Let's think about it for a minute. So now over here, this is important. I have this information. I know this is 100. I know this is theta, and I know this is 20. I could definitely find theta. I'm going to show you something even better. I can do this again without a calculator. I know that oh, I messed up. Messed up. It's not sine theta. Well, do I keep that in the video? I don't know. Let's see. I can see where I messed up here. Do you see it? What a halfwit. Sine theta is not equal y over 20. What a loser. Alright. Okay, well, this just shows you what happens in life. I don't know if I'm going to edit this out because this is real life. Okay. So right here. Let's go back to the drawing board. I don't know if I want to stop this video. Let's get to keep going here. Right there. Stupid. Tan theta equals y over 20. Opposite over adjacent, McPhee. Okay? 20 tan theta equals y. Now I'll take the derivative. Again, I didn't do anything wrong from here through. That's not the right relationship. Okay. So let's get back to the drawing board on here. And I kind of caught it here when I was doing this because I looked at this and said, that's tan. I'm like, where's tan? And something wasn't working out. Okay, back to the drawing board. Okay. So, taking the derivative of this. So, derivative of tan secant squared theta times the derivative of the inside, d theta dt, equals dy dt. Solving for d theta dt will equal dy dt divided by 20 secant squared theta. All good? I just don't like having 1 over secant squared, because remember, secant squared is 1 over cos squared. So if I write it like this, because I like cos better than secant, I can make that look a lot prettier. That just turns into cos squared theta dy dt over 20. All right, now we're getting there. Same idea, just I had the wrong relationship back here. So I have this, boom, 20 is already there. I just don't know what theta is. Looking at this picture, and I'll draw the picture bigger now. If this is 100, and this is 20, and this is theta, I have lots of information in this picture. I can even find that angle with a calculator, but if I don't want to use a calculator, watch how this works. Do you agree that tan theta here is equal to 100 over 20? Definitely. I even know sine theta and cos theta, because I can work out this hypotenuse. This hypotenuse length would be 100 squared plus 20 squared. It'll be the square root of 10,400. I messed up earlier. Let's just make sure I'm not messing up on the stupid small stuff. Okay, good. So sine theta is going to equal 100 divided by root 10,400. Cosine will equal 20 divided by root 10,400. So that's interesting to me, because I don't really need to know the angle. I just need to know the ratio. So right in there, in place of cos squared theta, I can write it as 20 over root 10,400 all squared, times dy dt, which is 50, all divided by 20. And I've totally bypassed having to even know the angle. That gives me 400. This gives me 10,400. That gives me 50. This gives me 20. Now I can just do a lot of simplifying. I would start with that. I can divide this by 2 as well. So here I'd have 2 over 52 times 5 over 2. These 2's cancel, and you get 5 over 52. And that is radians, because we're dealing with an angle change, radians per second. So how big is that? 5 divided by 52. That's 0.0961 radians per second. Now I'd like to know how big that is, because I don't visualize radians very well. Let's change that to degrees. So if I change that to degrees, multiply by 180 divided by pi, that ends up being 5.5 degrees per second. That's how quick the change would be. Okay, so hopefully that makes sense. My apologies for the mess up, but wasn't intended. Just been a long day. What time is it? Yeah, it's 6:30 at night or in the morning. Either way, that's late to me. So still doing math at that time, which you should be as well. Mistakes happen to the best of us. I could edit that out, but 2 reasons. Editing things on the computer takes me forever, in all honesty. And also, I think it's good to see mistakes that people make and catch them. So hopefully you were watching that video and screaming at me, and then I caught the error, and then you're like, oh man, he caught the error. Okay, hopefully you have a good day. Talk to you soon.